Writing out x times x times x times x times x wastes space. Exponents compress this sprawling multiplication into clean data. The bottom letter is the base being multiplied. The top number is the exponent, telling you how many times to multiply the base. Before we get to combining them, there is one absolute rule you need to know first, the zero exponent rule. Any base raised to the power of 0 always equals 1. It doesn't matter if the base is 5, a million, or a variable like x. If the exponent is 0, the answer is 1. Establishing these core definitions is the first step toward working with more complex expressions. Once you know the parts of the exponent, you can begin to manipulate how they interact with each other. When multiplying two terms, look at the bases first. If those bases match, you use the product rule. You keep the base exactly the same and simply add the exponents. For example, x squared times x cubed becomes x to the 5th power. Division works exactly the opposite way. This is the quotient rule. When you divide matching bases, you subtract the bottom exponent from the top one. So y to the 5th divided by y squared leaves you with y cubed. The underlying logic here is straightforward. When you multiply or divide matching bases, the math happening in the exponents shifts up one level into basic addition and subtraction. A common mistake occurs when raising a power to another power, like x squared all raised to the 3rd. It is easy to accidentally add these numbers, but when an exponent sits right outside a parenthesis holding another exponent, you must multiply them. X squared to the 3rd becomes x to the 6th. That same parenthesis logic applies to the power of a product rule. An outside exponent distributes completely to every internal base within those brackets. So xy in parentheses to the power of a becomes x to the a times y to the a. Let's test your ability to differentiate these rules. Look at these two problems on screen. The first is 3 squared times 3 to the 4th. The second is 3 squared all to the 4th power. Take 3 seconds to figure out which rule applies to which. On the left, we are multiplying matching bases, so we add the exponents to get 3 to the 6th. On the right, we are raising a power to a power, so we multiply them to get 3 to the 8th. Paying close attention to bracket placement is the only reliable way to know whether you should be adding or multiplying. The structure of the equation dictates the rule. Now we need to clear up a major misconception about negative exponents. Seeing a negative sign attached to an exponent does not mean you are dealing with a negative number. Instead, it's an instruction to take the reciprocal. You flip it to the bottom of a fraction, and the negative exponent transforms into a positive one. If you have 2 to the negative 3rd power, you move it to the denominator to make it 1 over 2 to the positive 3rd, which simplifies cleanly to 1/8. A negative sign on an exponent is not an indicator of mathematical value. It is simply a set of traffic directions telling the base to cross over the fraction line. We have reached the final and most visually complex concept, fractional exponents. It looks intimidating to see a fraction hanging in the air, but the mechanics are entirely predictable. Every fractional exponent has two distinct functional roles. The top number is your power. The bottom number is your root. Think of it as power over root. Let's apply that logic to 8 to the power of 2/3. The bottom number is 3, so we need the cube root of 8. The top number is 2, so we will square that result. The cube root of 8 is 2, and 2 squared equals 4. The fractional logic resolves right back into a whole number. This infographic displays all 7 exponent rules gathered in one place, ranging from the product rule down to fractional exponents. Screenshot this master list. By systematically applying these 7 distinct laws, you can begin to reduce complex exponential terms into their simplest possible forms.